Good. Properties of rational functions. Now, we'll be considering the last case in the series that we have been doing so far. So, ensure you have watched case 1 and case 2 of this series of videos. So, this case we'll be considering the case when the degree of the numerator of a rational function is greater than it's greater than the degree of the denominator. So that is, if you have a rational function, say g of x equals p of x divided by q of x. So when the degree of the numerator is greater than the degree of the denominator. So we want to consider how to find the properties of this kind of rational function. So the example we'll be considering is g of x. So the example we'll be considering is g of x equals x squared plus 2x plus 1 divided by x negative 3. So this is the example that we'll be considering. So anyway, the very first thing you want to do to find the properties of this rational function is to factorize both the numerator and the denominator. Like you know, that has been our first step. So far so good. So when you factorize x squared plus 2x plus 1, so what you'd obtain is x plus 1 into x plus 1 divided by x negative 3. So this is what you obtain. So to find the domain, that is the domain of this rational function, so we said it's just the set of all real numbers excluding the zeros of the denominator. That is excluding 3. And then secondly, to find the vertical asymptotes, so what you want to do is you want to ensure that the first step you want to do is to write the rational function in its reduced form, that is x plus 1 divided by times x plus 1 divided by x negative 3. So since nothing crosses out, so this is the rational function in its reduced form. So the next thing is the zeros of the reduced form is going to be your vertical asymptote. So the zeros here is x equals 3. So this is your vertical asymptote. So again, you note the vertical asymptote is not a number, it is an equation. This is an equation. It is an equation. So 3 is not, I repeat again, 3 is not a vertical asymptote, but x equals 3 is a vertical asymptote. It's the equation of a line, not just a number. So the third one, which is the horizontal asymptote. So as usual, this case here, you'd observe we said we're dealing with the case when the degree of the numerator is less than the degree of the denominator. So the degree of the numerator is actually 2. You can see here is 2. That is what we have here, is 2. That's the highest power of the polynomial in the numerator, while the highest power of this polynomial here is 1. So the degree here is 2, which is greater than the degree here. So this kind of case is a little different, and then where its difference comes into play is in finding the horizontal asymptote of the rational function. So how do I mean basically? Now, according to the last 2 videos we've done so far, whenever we want to find the horizontal asymptote, what we usually do is we wrote x squared plus 2x plus 1 divided by x negative 3. We said to find the horizontal asymptote. The horizontal asymptote simply means the long-term behavior of the rational function. To find the long-term behavior of the rational function, the very first step you want to do is you want to approximate the rational function by the leading terms. So this is the leading term here, this is the leading term here. This is the process which we had done in the last 2 videos on this series. So, and then this will give us x squared divided by x, which is going to give us x. Now as x tends to infinity, this number here also tends to infinity. So but then it doesn't make sense to have y equals infinity as a vertical asymptote. So this does not make sense. So how then is the best way to handle a situation like this? I'm going to show you that. Now, to explain how to find the horizontal asymptote, let's just have a very quick review of how to do long division. Now, whenever you have a number 7 divided by 3, you recall that this is the same thing as 3 divided by 7, that is 2, remainder 1 over 3. Now how did I obtain this? Now this is how we do it. So you have 3, which is the divisor, and then you have your 7 here. Now 7 divided by 3, it gives us 2. 2 times 3, that is 6. 7 minus 6, that gives us 1. And then since 1 is not divisible by 3, so this is going to give us, that is, we have 7 all over 3 is going to be the quotient, which is 2 plus 1 divided by 3. So this is what we obtain for normal long division. So let us see how we can go about finding writing this rational function in this format here. So what we have here is we have x squared plus 2x plus 1 divided by x negative 3. So this is exactly what we have. Now to do the long division, just like we did here, so we'll have the divisor out, that is x negative 3. So this is the divisor. Then we have x squared plus 2x plus 1. So whenever you're dividing for polynomials, the only men in charge, that is the ones that do the division, are the very first term, that is the leading terms. The leading terms are the ones that undergo the division. So x in x squared, that is x squared divided by x, you obtain x. Then you now multiply back x times x, that is x squared, then x times negative 3, that is negative 3x. And then like we did here, we subtract. So you subtract, and then we subtract also here. So all terms you subtract. So x squared negative x squared, that's 0, plus 2, negative is plus. So this is 2 plus 3, that's 5x, and then plus 1. So again, since 5x is divisible by x, we could still continue the process. So 5x divided by x, that is 5. Then 5 times x, that gives us 5x. 5 times negative 3, that gives us negative 15. And then we subtract like we did above. So all terms are subtracted. So 5x negative 5x gives us 0. Then plus 1 negative 5x, right? Negative 5x, that's going to give us what's that going to give us? 16. That's going to give us 16. But then 16 is not divisible by x, so that implies that we have to stop here. So like we did here, so that implies that x squared plus 2x plus 1 divided by x negative 3 is the same thing as, so like we have here, the quotient is 2, so the quotient here is x plus 5 plus the remainder here is 1, the remainder here is 16, divided by the divisor is x negative 3. So I have been able to write the rational function in a new format. So let's now find our horizontal asymptotes. So to find the horizontal asymptotes, so what I have here is x squared plus 2x plus 1 divided by x negative 3. So we've written this in a new format, which is x plus 5 plus 16 divided by x negative 3. Now what you'd observe here is we said to find the horizontal asymptotes. The horizontal asymptote is just simply the long-term behavior of the rational function. Now as x becomes very large, you'd observe that the number at the denominator here, it blows out. That is, x becomes infinity here, so this whole thing here goes to 0, and then what you'll be left with is going to be x plus 5 plus 0, which is x plus 5. So therefore our horizontal asymptote is y equals x plus 5. So now whenever you have reached this stage, it's no more a horizontal number anymore, because this is the equation of a line, which is not a horizontal line, because you know the form of a horizontal line equation of a horizontal line is y equals say 3 or y equals 4 or y equals a constant. But then this has an intercept and it has a slope, so it's not a horizontal line. So because of that, we can't call this kind of asymptote a horizontal asymptote. Instead, we call it the oblique asymptote. That's what it is called. So for this kind of a question, we do not have horizontal asymptotes. So let us see how this can be shown on a graph. So let's say we have a graph. So let's switch it on. Okay, I used this previously, so let's go back to the Y editor. So this was the graph we used. Let's clear this. So what we have here is we have x squared. So let's go, we have x to the power 2 plus 2x plus 1, now divided by x negative 3. So this is the function we have. So let's see how the graph looks like. So we go to graph. This is our function, and then this is our function here. So this is exactly what we observe. We observe that if we go back to the question here, what you'd observe is we only have one vertical asymptote, which is x equals 3. So that is why you just have a single line here, which is x equals, you can see this is 1 2 3, that's x equals 3, and then we have the graph here. So let's just be sure that we have included all parts of the graph. So let's go to the window. Let's go to the window. So we have negative 15, 10, and then let's increase the values in the y-axis. So let's call this negative 10, so you can have a clearer picture of the whole thing. So let's graph it again. Yeah, so we can see the way the whole thing is going. X equals this. So this is a very good picture. But then what you'd observe is you might begin to wonder, in the graph here, or in our solution here, we have the oblique asymptote to be y equals x plus 5. But then if you look at the graph here, it's not showing. You can't really see it. I don't know, for some reasons the TI-89 is not showing. Maybe it's in the setting. I don't know for some. But for now, I've not been able to figure the thing out. But I'm going to go back to the editor. So we are going to punch in y equals x plus 5. So we'll see the trend. So we have x plus 5. Yeah, so let's plot the two of them together. So we'd see, yes, so this is the oblique asymptote. You can see how the graph goes near and then passes the whole thing. Alright, so I do hope you really understand the synopsis behind the whole stuff. Alright, that brings us to the end of this question. But then one lesson which you need to learn, or which is something which is quite important that I feel I should let you know, is that for the case of the oblique asymptote, or let me say for this case, when the degree of the numerator of a rational function is greater than the degree of the denominator, you always have an oblique asymptote. So whenever the degree of the numerator of a rational function is greater than the degree of the rational function, the denominator of the degree of rational function, then you always have the degree of you always have an oblique asymptote. Yeah, and then that completes the problem. So before I round this up, let me also tell you that, but for the case when the degree of p of x, that is the numerator, is less than the degree of q of x, we said the horizontal asymptote is always y equals 0. For this case, is always oblique, and then the last case is just a constant. Alright, that completes the whole problem. Thank you for watching.